Thank you very much. Hopefully there'll be something for everyone in this. Now, especially for those who haven't used a non-linear before, let's run through a few basics. You're probably familiar with this sort of thing, but yeah, just make sure we cover everything. So linear analysis. A lot of assumptions in there. Displacement strain relationship is a linear thing. Stress strain relationship is linear. Both are valid if the displacements and the strains are small. And the equilibrium conditions, the forces versus reactions, are established at the original non-deformed geometry. Which end results, equilibrium is linear, load displacement is linear, load internal forces are linear, which means you can multiply the loads by a factor and the end result is appropriate. The thing to remember is that because everything's based on the original non-deformed geometry, if the deformation and strains are large, then the results will not be accurate. You'll get results, but they won't necessarily be accurate results. Conversely, if we look at non-linear analysis, non-linear analysis occurs if if you've got a large displacement, we call geometric non-linearity. If you've got plastic yielding of your material, or if you've got elastic material but with very large strains, such as rubber or something like that. Yeah, not normally a structural material, but we look at those sort of problems. So the end result is the equilibrium equations and the load displacements and the loading forces relationships are not linear, which means that you can't multiply the results by a factor after you've analysed. You can't combine the results, and the structural response, the axial loads and so on, may be path dependent. Now what we mean is, we'll look at that in a moment. So first of all, look at geometric non-linearity. I mentioned before, this is a linear analysis. Everything's based on the initial geometry, so the reaction F is equal to the load P, reaction V is equal to load Q, and the moment is equal to Q times the height. Good first year stuff. But when you get onto non-linear analysis, you're getting a large deflection, which means the reaction F and V are both a function of both the loads P and Q, but also the moment is a function of Q times the height plus P delta, the load P times the deflection. So, examples. Let me go to GSA and I'm going to call up a 3-pin beam. Now I'm using a lot of models I created earlier in this particular today, just to keep things moving along. Okay, there. Now, the thing about this beam is that, as you can see, it's a two element beam with pins at the ends and in the middle, which means that, of course, it won't solve. As you know, this cannot take any bending moment, and therefore a linear analysis will not work at all. But if I go and create not linear but a non-linear analysis, and I take these defaults, we'll come back to the load increments later, and I'm going to add in my load case. It's going to ask about magnification of graphical views and so on, and rearrangement of views. Non-linear analysis can take a while, so that there's a certain amount of rearrangement of views, so you can see what's going on better. Let's analyse that as happens. This was a nice quick one, and we can see that this beam has defect. This is a one-to-one deformation, and if we look at the bending moments, now the bending moments will look a bit strange, but they are minute. These are just residuals left over from the convergence criteria, but you see they are tiny. But what we've actually got is this load has been taken up in tension in these elements, having because these beams have deflected down, as you can see them there. Now, talk about deflections. You can deal with some quite seriously large deflections. I mean, here we have a cantilever, but this cantilever is pinned at one end. Now, again, standard linear analysis and a lot of non-linear analysis from other programs won't be able to cope with this, but with GSA methods, it can. Let me just run through, make sure deformation set to 1, and analyze that. And we can see, as you expect, this pin cantilever has rotated until it is in equilibrium with the load, i.e. it's hanging straight down. So with the GSA non-linear analysis, you can deal with some actual mechanisms, as long as there is a sort of final resting point in place. Yeah, so some way that the structure can sort of finally sort of balance the loads. Now, now with other structures, sometimes there comes a choice where you might want to use linear, you might want to use non-linear. And if I enlarge this and we look at this cantilever, and we can see I've got vertical load on top, horizontal load mid-height rather than at the end, as we had in the PowerPoint. And these loads, these are just nodal loads. And if I just set this somewhat small, so nominal loads, and under here I have got a static linear analysis, a P delta linear analysis, and a non-linear. And if we just analyse those three, the end result, as you might expect, axial shift, and annotate those, and I'm just going to modify those. So we're just seeing integers. Not that one. Just tidying up the display makes it a bit easier to read. So we can see under static analysis, as you expect, the axial load is equal to the applied load, the shear force is equal to that load, and the bending moment is equal to that height. This is a 10-meter high column, and the P delta and the non-linear analysis all giving exactly the same results. Now, at the moment, if I look at my saved output views and tap that on the left, tap that on the right, at the top of this column, I've got node 1, we get a deflection of 0.7 millimeters. Now, height of a 300, we could take this up to about 33 millimeters. So what I'll do is I'll just multiply those values and use a factor multiplied by a factor of 50 and rerun those three analyses, and we can see the deflection to the top. Okay, allowable deflection for 33 mil on the limits, really linear there, but you notice that the linear, the P delta and the non-linear analysis are basically given the same deflections, and if you see down here the the axial loads and bending moments and so on are essentially the same, and there's very little difference between the three analyses. Now note, I've also got a lowercase c1, which is the non-linear results take away the linear results, so you can see the difference between the non-linear and linear, and the differences are quite small at the present. Now, if we instead push this beyond sensible values to, say, 2000 kilonewtons, and this is obviously going to be quite way beyond deflection limits, and we'll see that for we can see that for the linear analysis we're still getting linear responses in the shear forces, axials and so on. And let me just set that deformation to 1. The P delta is much larger, and we're getting additional moments and additional shear forces. The axial load is remaining constant, and notice note the deflection at the top, there's very little vertical movement on the P delta. We go on to the non-linear, we're actually getting a rotation of the structure, though the moments and so on are similar to the P delta. If I actually show all three, A1 to A3, on the one diagram, we can see that the rotations of the structure and so on are similar between the P delta and the non-linear, but the displacement at the top is quite different. Basically, this means P delta analysis is okay at moderate deflections, but when you get onto very large deflections, P delta analysis is not necessarily going to give you trustworthy results, because in theory, with this deflection, the P delta column has actually grown rather than shrunk, which of course is slightly nonsensical. So, non-linear elements. There are a number of non-linear elements in GSA. Struts and ties, may well be quite familiar with these. These are compression only and tension only 1D elements. We also have cable elements, which are like ties, but they have some quite strange properties, which I shall show you in a moment. And we have fabric elements as well, which are tension only 2D elements. So let's look at these in action. Let me close this and open up. Well, let's just create a strut and tie model. Plane frame. And I'm just going to draw in elements there, and copy them, 2 copies, cunningly using the polyline to copy the elements across, keeping the spacing. And what I'm going to do is I'm going to take those 2 elements and modify them to being bars, so axial only. Those 2 there, I'm going to modify them to being struts. And these 2 here, I'm going to modify those to being ties. I'm also going to modify those 3 elements so that they just have bending releases on them, which you see. So these are pin endings, so you won't get moment traffic. I could set them all to bars, but let's leave them that for the moment. And if I add in a node load up there, doesn't matter what the load value is, let's just set it to 1. And these points down here need to be pinned, and we need to give a section. And I'm just going to pick a small beam size. So we'll analyse. The important thing is, if I analyse this, we note that we get some warnings about, because we've got struts and tie elements, the solution could become iterative. But it has completed. Now, if we look at the results, and if we look at the axial force in these elements, and look at the deflections, you'll see that the strut is picking up load, the tie is picking up load, the bits in between are not, and obviously bars, they are both taking up load. And if you imagine, if we were to do a load case, let's do a combination case where we say -1 times that load. The results are quite clearly nonsense, because we'd end up with compression in the ties and tension in the struts, which is ridiculous. Yeah, you cannot. This is example where the load path is dependent on the load itself, and therefore it's quite inappropriate to start multiplying and sort of negating the values and so on. Now, also mentioned about cables, and again I'll sketch something in. What I'll do is I'll go from there to there to there. And what I'll do is I'll modify those two to being ties, and those two nodes there, I'll pin them, and need to create a load down there. Node loads X direction 1 and Y direction -1. So we've now got a load in line with that tie. And let's just give it a section as well, so we can get some forces out. So if we obviously a linear analysis won't work on this, because it's a tie without any constraints. It's stabilized by the load ever on, so we have to do a nonlinear analysis. Take defaults, not worried about showing the deformation, because the end deformation will be just in a straight line, a slight stretching. So the axial loads and the reactions, okay, resolve reactions, and just annotate. Well, that we can see there's a load of 1.4, the axial is 1.4, the reaction is 1.4. Straightforward. Now, those are ties. Cables are slightly different. Now, the thing about a cable is that when you have multiple elements of the same cable property, they are treated as one continuous cable. Note, they do have to be continuous, they can't have any splits or separations or so on in them. But when you do have that, so we now go black, what will happen is the axial load will remain constant in this cable, which means that these nodes, intermediate nodes, are free to move along their length. Now, let's give some property to this, And when we run the analysis now, you can see that the axial load is the same as the apply load, but it goes round the corner and down to this support point down here, whereas this point is now has a much larger reaction. Nodal points on cables are essentially like pulleys. So if you want to model a crane lift or something of that order, then they are very good for that. If you want suspension bridge, when you want to model the catenary shape with various things like that, then they can be very useful for that too. But use with caution, because the end deflected shape might not be quite what you expect. Oops. Now, we've got material non-linearity in GSA. Okay, this is a little sketch of a steel stress-strain relationship, approximately, I know. And you can see we've got the elastic zone, yielding, plastic plateau, strain hardening, and then onto failure. In the GSA model, we have something a little bit simpler than that, which is just a linear relationship up to yield point, and then straight plastic, with no final failure point. This does mean that you can create plastic hinges and so on in GSA. In fact, let's go and open one up. If I just get rid of that and find one I prepared earlier. So this is a two-span beam with a UDL load thereon, and if I run a linear analysis, you'll see what we get is bending moments where it's higher in hogging and not so high in the spans. But if I call up the beam stresses, you'll note that the stresses are actually higher than the support, but they are higher than steel will allow. And what we've done in this particular element is I've set up an elastic plastic material property. Let me just delete those results in a minute. We have a number of material property options. The default is elastic isotropic. You can do orthotropic now, have the different properties in different directions. But this is the elastic plastic, which means when we go into the properties, we have the yield stress in there. It does mention an ultimate stress, but that is not used directly within GSA. If you're using GSA as a preprocessor for something like LS Dyna, then you can use then that figure will then come into effect. So what this means, if we look at our section is using that material, and again I'll just rerun the linear analysis, but I'll also call up a nonlinear analysis. Just take the default loads, don't bother multiplying that. And we can see that if I just rescale that, under the nonlinear analysis, and you see from port 2, we've had material yielding. So the hogging point has reached its maximum moments, and we're getting yielding there and yielding at the mid span. And if I just switch the contours off the moment, we can see that the bending moment is quite similar between the support and the span. hasn't quite gone to the same because the plastic hinges aren't fully formed in the spans. They're very close to fully formed, but not quite. If the loading was such that the hinges fully formed in those supports, this structure would have collapsed, or the analysis would say non-convergence. We also have buckling. Now let's have another show of hands. Who's used GSA for buckling analysis? Okay, any more? Okay, let's have a look. Okay, very even split between those who have and those who haven't, and those of course who haven't used GSA at all. Interesting. So, so buckling. There are in GSA we have both linear buckling and non-linear buckling. Linear buckling is also known as eigenvalue or modal buckling, and the non-linear is also known as member buckling. And the non-linear can take into account the material properties. So linear buckling first. As you know, when you apply an axial load onto an element, its stiffness reduces, and what the analysis is trying to do is to find the multiplying factors on the loads such that element stiffness reduces down to 0. Now, the notice here, the shear force V has very little effect on buckling load capacity. Doesn't have no effect, just has little effect, because like all linear analysis, the equilibrium is based on the initial geometry, and we're looking for a load factor, and so this, because the structure is assumed to be equilibrium at any deformed position, it's the most shape is good, the load factor is good, the actual deflection is not something to be taken in notice of. The maximum deflection will normalise to 1 meter, the maximum deflection will normalise to 1 meter, and the other deflections will follow suit. But when we go to non-linear analysis, this is when we increment the loads up to a failure point. What you're getting is the actual deflection of the structure and the deflection load relationship. Now, the difference between these two is, well, if you've got linear buckling, then displacement is, well, there's no relationship between this displacement and load. With elastic non-linear buckling, you'll get the displacement gradually increase and up to the buckling load, or nearly the linear buckling load. You might not get complete agreement between the linear and non-linear buckling, and if material non-linearity is taken into account, then the buckling load capacity will be much lower. So obviously you're getting plastic yielding of the structure. So examples. Let me just tie this up and open up column model. Now this column model has a point load at the top, restraints at the top from strain structure, sorry, a mid-height minor axis restraint, and a pin support at the bottom. And this load at the top is a unit load, just a single kilonewton. And what we can do, if we create a new modal buckling analysis, I'm just going to ask for 4 modes on this to begin with. It is an iterative method, so you might want to include a cut-off point if the analysis is going on too long. Load factors are interesting. If, as I mentioned, you're looking for axial loads where the stiffness goes to 0. Now if that load up there was a tension load, we would then get a negative buckling factor, load factor, which of course is nonsense. Tension loads don't buckle structures, any compression loads do. So it can be worthwhile having in a lower cutoff point to 0, which means it will just ignore any of those anomalous negative buckling load factors. You can also have an upper factor. Now this is a unit load. If you're working to using working loads or service loads, you might say, okay, I want an upper cutoff factor of let's say twice or 3 times the applied loads. I'll take the loads that I'm using as a load case or results case, and if we analyse that, getting a warning here about eigenvalues being close to the mode. Let's have a look at the buckling details. Tap that to the left, tap that to the right, and we see we've got load factors of 642, 819, 1385, 1386. Now these two are very close. Now let's look at the deflection. So mode 1, that looks quite sensible, a nice major axis bending. Mode 2, minor axis bending, that's good. Mode 3, oh dear, we've got strange torsional failure, and mode 4 likewise a strange torsional failure. Now those are nonsensical buckling modes. Let me go and prevent those by editing the analysis task. Now under the advanced options, under geometric stiffness, I can say I can suppress these torsional and lateral buckling terms. Basically, I'm saying one of the elements can't really do lateral torsional buckling, and the torsional buckling I'm not interested in. So I'm just going to rerun that, and what we now get is more separated load factors, and we see we're getting mode 3, sort of minor axis double buckle and major axis double buckle. So more sort of sensible looking buckling shapes. Now these are all the ways that it could possibly buckle, but we can see that mode 1 is the way that it will buckle. You might have a number of closely spaced modes in a more complex structure. So what I'm going to do now is I'm going to do a nonlinear buckle on this, and to help it on its way I'm going to take this buckle shape and update the geometry so that this buckling becomes an initial imperfection. I'm going to use the tools, manipulate model, create new model from deformed geometry. And so I'm going to take mode 1, and I'm going to say the maximum displacement is going to be 5 millimeters. And so what we now get is, if I look at that node there, you can see that the node is now 5 millimeters off from the center line. Now do a new analysis, which is a not a modal but a member buckling, and the elements I'm interested in, oops, let me call up members 6, 7, 8 and 9. Let me start that again. Member buckling 6, 7, 8 and 9. These are the ones I'm interested in buckling. I'm going to create a default load case, which is my unit load at the top, and well, I could take the magnify. Let's analyse that. And you can see it's so again problems there. It's not entirely happy. That is, let me unlock that scale. You can see the structure has now buckled. Now that buckling shape doesn't look particularly good. I think we probably need to split this up into more nodes. Now note, of course, for the buckling I do have the mid-height nodes on these elements to get reasonable results. I suspect this one might have to do it more, but in the meantime let's have a look at the the results. Now, you notice on the report view, it says determine the buckling load capacity of the member, plot the axial force deflection, and you find that under the chart views. And remember the modal buckling capacity was about 640, and if I ask for the call that's the nearest point, you see this, we get a maximum buckling load of 635 on this chart, with not so much detail on the last bit where it goes quite suddenly, but from this chart you can sort of work back to a safe working load where the where the displacements are not excessive. Now, apart from general buckling, we can also look at snap-through type analyses. I mean, here we have an arch, which I've got an asymmetric load on the arch, and let's just go and open up this existing analysis task where it got so non-linear static. And important thing here is we're going to automatically increment the loads. So we're going to start off at 10% of the loads and then gradually ramp up the loads until something interesting happens. Now, to make sure it stops, we've got a limits. Now in this case I've got a displacement. No date is that one at the top. I'm going to say no date once it moves vertically by a meter, then stop the analysis. Similarly, I could also apply a maximum load factor as well. And if I just step back down to its original starting point and run this analysis, you see in the report view the loads are gradually increasing, and you can see from the deflected shape that this arch has indeed snapped through. And you can see as a load factor from the report view here of about 4.3. Again, we can see this maybe a bit clearer in the chart views, and you can see, yes, this is deflection. Deflects upwards to begin with and then snaps through at about load factor about 4.3. Now if we had allowed this analysis to continue on from here, you see this load displacement graph would then go on an almost vertical line up from this point, because this has become a change from a compression only structure to a tension only structure. So combinations. If you're not familiar with nonlinear analysis, this can be a confusing area because a lot of it's very familiar but not quite familiar enough. The thing to remember in GSA is that you apply loads in a load case, and when you analyse them they're put into an analysis case. Now if you just hit the default analyse all button, it will create one analysis case for every load case. Give it the same name, give it the same number, and so they look pretty similar. And then you can multiply and combine them together and so on. Now, yeah, so here we are. Load cases, analysis cases. Note the load cases begin with an L, analysis cases begin with an A, combination cases begin with a C. And being a linear analysis, you can multiply the analysis cases and add them up and then produce an envelope. But when it comes to nonlinear analysis, not acceptable. Instead, within the analysis, each analysis case, you then have to multiply and add the load cases together for the particular analysis task. Remember, because the loads are dependent on the final geometry and the load paths can change and so on, so this is quite important. And the combination cases, the only combination case you're allowed is an envelope case. Okay. Now, dynamic relaxation itself. Now, yeah, GSA uses a method called dynamic relaxation, which is different to, say, the Newton-Raphson method. And what essentially it means is that the structure is set to vibrate, and the stiffness and loads are replaced by masses, and what you have is, imagine this is a weight on a vibration on a wire. When it's at these sort of extreme values, the speed of this is 0, the energy of it is 0, but the acceleration is maximum. Whereas when we have the equilibrium position, point at rest, its speed is maximum. It's travelling from here to here, or vice versa, but it's under 0 acceleration. You know, the forces are all balanced out, but it's got maximum kinetic energy. Now, because this is dynamic, you need to damp these movements down. Viscous damping is the default, and viscous damping is a bit like having something in oil. The resistance to the movement is proportional to the velocity of those nodes. So the faster something is moving, the more out of balance it is, and therefore the more damping is applied. There's also a thing called kinetic or artificial damping, and what this does is it says, okay, the equilibrium position is when the various nodes have peak kinetic energy. They're moving fastest, minimum forces. And so what it does is at each stage it finds the points where kinetic energy is maximum, readjusts the geometry to those positions, and then carries on the analysis from there. So it can work quite well. Sometimes the kinetic damping can solve quicker than the viscous damping. It all depends. Now, when it comes to viscous damping, there's a concept called critical damping. Now, if there's no damping at all, the structure will oscillate back and forth forever over time. Critical damping is just the right amount of damping to find the answer quickest. If you have just a little bit less than critical damping, the deflection will all overshoot and then kind of gradually come back to the equilibrium position. And likewise, if the damping is larger than critical, it won't overshoot, it will just take longer to reach the point. And GSA is generally very good at finding the damping value, but there are times when it struggles to converge, and therefore it allows you to go in the report view, and not the report view, the little toolbar that comes up with the nonlinear analysis, and you can then go in and tweak the damping values to enable you to get the analysis to converge. So, a few examples of GSA nonlinear analysis in action. Okay, 4 years ago, the Beijing water cube. Particularly interesting point here is the ETFE cladding. ETFE is like a foil, and it's pressurized, and so this is tension only fabric. And so you need the nonlinear analysis to analyse both the original form finding, the deflections and yielding under pressure loads, but then what happens to the structure once the wind blows on the structure, snow if that's allowed, and so on. Another fabric structure, which is a conic structure from the Museum of Modern Art in New York from a few years back, and you can see the mylar fabric in this case, which is made up of all those triangles, with edge cables to keep everything tensioned, struts to hold things in place, and plus a toddler in the foreground to make sure everything works fine. Larger structures, stadium, Khalifa Stadium. Note the cable net supporting the fabric roof, so both the edge cable keeping tension there and the cables pulling it up into that arch. Likewise the arch on the far side, which is cable supported for the lighting rigs. Another option, the Melbourne Cricket Ground. See the cables supporting the roofs, but the cables are supported by these flying struts, but the flying struts are also supported by the cables, all carefully balanced. Singapore Fly, a Ferris wheel, or obviously the cables working in tension. Something slightly more unusual. This is more a sculpture over in Washington. The main locus on this is wind-induced vibration. But of course, being reinforced concrete, when it deflects, concrete cracks, the stiffness changes, and therefore the vibration changes. And so, quite a lot of iterative analysis required to solve this one. Some public buildings: National Assembly for Wales in Cardiff Bay, or the Royal Ontario Museum. Quite an interesting looking structure. I do like that one. Some bridges: Carilpa Bridge in Brisbane. It's a 10-secretary structure, and you see the cable supporting the flying boom supporting the deck, and so on. This one also won quite a few structural awards in Australia. And the Infinity Footbridge, Britain's longest footbridge, I think 120 metres for the larger span, won Institution of Structural Engineers Supreme Award back in 2009, and a whole host of other awards as well.